let us continue with the second lecture in module 3, where we are going to talk about the flammability characteristics. This is the second lecture in module 3, where we are focusing on risk assessment and management and accident modeling. We already said few characters are important for understanding the flammability characteristics better. One is what we call auto ignition temperature. Other is what is called the flammability limits. Let us talk about the flammability characteristics in detail, in which the foremost thing is the flammability limit. Flammability limit actually is a range of vapor concentration. It is a range which could cause combustion. In the presence of ignition source. Essentially, there are two limits. One is what we call upper flammability limit, which is UFL. Other is lower flammability limit, which is LFL. LFL actually is a limit below which the mixture will not burn. What could be the reason for this? The reason is the mixture is too lean, so it cannot cause ignition. Upper flammability limit is the limit above which the mixture will not catch fire. The reason is the mixture is too rich. So, essentially flammability limits is actually the range between UFL and LFL, because it is that region between which a mixture can catch fire. The next property could be, interestingly, limiting oxygen concentration. It is the minimum oxygen concentration. It is defined as the minimum oxygen concentration below which combustion is not possible. To activate combustion, you actually need minimum O2 presence. Okay. If the oxygen concentration is below a minimum required value, the mixture may not catch fire even in the presence of ignition source. Generally, this is expressed as volume percentage of oxygen. Sometimes it is also called MOC, that is minimum oxygen concentration. It is also called sometimes as maximum safe oxygen concentration, which is MSOC. So, LOC can be referred as MOC or MSOC. It is actually the minimum oxygen concentration required for a mixture to catch fire. As we said earlier, the important consequence or effect of an explosion release is it can result in a shock wave. Let us see what is called as a shock wave. A shock wave actually is an outcome of an abrupt pressure wave. This is actually an abrupt pressure wave moving through a medium. Interestingly, a shock wave in an open air is followed by wind to activate the velocity. This is called blast wave. The blast wave is the one which follows the shock wave, which is activated by wind. One of the important vital characteristic of a shock wave is that one of the important characteristic is pressure increase in shock wave is so rapid that the process is almost adiabatic. There is another important consequence which comes from explosion, what we call as overpressure. Overpressure is nothing but an additional pressure imparted on an object by a shock wave. Let us quickly see the consequence or the range of the flammability characteristics. Kindly pay attention to the figure shown on the screen now. The screen shows a graph which plots temperature on x axis and flammable vapor concentration on the y axis. The red line indicates saturation vapor pressure curve, whereas the green and maroon indicates the lower flammability and upper flammability limits. Interestingly, as the temperature increases, the upper flammability limit keeps on increasing and the lower flammability limit keep on decreasing from the original value, and that increases the range of flammability, because flammability is actually the range within which it can catch fire. As the temperature increases, you will obviously see the range of a mixture which can catch fire is widened or increased. However, the gas or the liquid will remain non-flammable above upper flammable limit and again non-flammable below lower flammability limits. It is at that temperature which auto ignition is required. It means the mixture will not require any external ignition source to catch fire. So, it is that temperature which is indicated as auto ignition. So, auto ignition completely lies within the flammable limits of any given mixture. We have also seen the flash point, which is an important flammable characteristic of any given mixture, which has been now put together in all terms in a single graph, as you can see from the curve now. Let us talk about flammability liquids, characteristics of liquids. The flammability characteristics of liquid are experimentally determined by a setup called open cup method. So, they are generally determined experimentally by open cup method. However, the flammability characteristic of liquid can also be expressed using analytical relationship, which I will write now, if you know the constants A, B and C. The flash point temperature Pf can be computed for a given liquid, for any liquid, if the boiling point is known. Let us say both the temperatures are in kelvins, then flash point temperature of a liquid is simply given by A plus B into C by Tb, the boiling point, exponential to the power of minus C by Tb divided by 1 minus exponential to the power of minus C by Tb the whole square, equation 1. If I know the boiling point of the liquid, I can easily estimate the flash point if you know the constants A, B and C in this empirical equation. So, for different chemicals, these constants A, B and C, which are used to estimate the flammability characteristic of a given liquid, can be easily given and seen in the literature. So, please pay attention to the table shown on the screen now, which gives me the values of these constants A, B and C for different chemical group, as you see in the list here: hydrocarbons, alcohols, amines and acids, ethers, sulfur, esters, halogens and aldehydes. So, the constants A, B and C are available. Substituting them and knowing the boiling point temperature of the liquid in Kelvin, one can find the flash point temperature of the liquid in Kelvin again, and once you know the flash point, one can easily find out the upper and lower flammability limits or characteristics using open cup method, which can be easily estimated. Let us talk about flammability characteristics of vapor and gases. The flammability limits of vapor can be also experimentally determined in a closed vessel apparatus. So, they can be experimentally determined using a closed vessel apparatus. Alternatively, one can also find the flammability limits of mixture of gas and vapor using the empirical relationship. So, the lower flammability limit of the mixture of vapor and gas can be simply given by 1 by sum of yi by LFL of I, and I is the sum here, equation number 2. Upper flammability limit of the mixture can be again given by the same equation, of course substituted with yi by UFL of I varies from 1 to n is the number of gases or vapors considered for the analysis. So, LFL I is the LFL for the ith component, is the lower flammability limit of the ith component in the mixture in terms of volume percentage. Yi is actually the mole fraction of the ith component on a combustible basis. N is the number of combustible species, which is considered for the summation. So, if you know the LFL and UFL of ith components present in a given system, and if you know their mole fraction on the combustible basis, one can easily find out the LFL and UFL of the complete mixture or the limits of a given mixture, which is a mixture of gas and vapor. Subsequently, the flammability limit behavior depends on both temperature and pressure. Depends on temperature and pressure. When the temperature increases, upper flammability increases, while lower flammability decreases, which makes the flammable range of the fuel or the mixture more. So, increase in temperature will increase the flammable region more. So, this increases the flammable region or a range, one can say flammable range. Okay. So, coming to pressure, as pressure increases, upper limit increases, whereas pressure has no significance on lower flammability limit at all. So, no significance. On the lower flammability limit. Therefore, the relationship of upper flammability limit with that of pressure can be given by a simple equation. Upper flammability limit with that of pressure can be simply upper flammability limit plus 20.6 log P plus 1, where P is the absolute pressure in, let us say, megapascal. Interestingly, we have now agreed upon that to estimate the flammability characteristics or probability of catching fire for a given mixture depends on the upper and flammability ranges, limiting oxygen concentration and autoignition temperature. There are various characteristics based on which one can estimate what is the probability that a given mixture of gas or vapor or liquid can catch fire. So, one can also estimate the flammability limits using stoichiometric balance. Flammability limits can also be estimated using stoichiometric balance. Now, for many hydrocarbons, in general, the LFL and UFL, the lower flammability and upper flammability, are essentially functions of stoichiometric concentration, what we call as CST of the fuel. So, let us say a general equation which can be useful in computing this relationship. Let us say Cm hydrocarbon, H with concentration X and oxygen with concentration Y plus oxygen concentration in terms of Z will give me carbon dioxide plus X by 2 concentration of water. That is a general stoichiometric relationship which is indicating combustion reaction. In that case, the stoichiometric concentration which is given by (21% by 0.21 plus the Z value. Z can be calculated where Z can be computed as Z will be m plus 1/4 of x plus half of y. We have something called stoichiometric balance. Stoichiometric balance gives the relationship between the quantities of substances involved in a chemical combustion reaction. Stoichiometric balance gives the relationship between the quantities of substances involved in a chemical or a combustion reaction. This is typically a ratio of whole integers. This is a ratio of whole integers which includes the calculation of quantitative relationship of the reactants and the products of a balanced chemical reaction. So, you need to have a balanced chemical reaction. From the balanced chemical reaction, one can identify the quantitative relationships of the reactants and the products. Based on which one can easily find the stoichiometric concentration. Let us say LFL, the lower flammability limit, can be given by 55 by 4.7 m plus 1.19 x minus 2.38 y plus 1, whereas the upper flammability limit can be given by 350 by 4.7 m plus 1.19 x minus 2.38 y plus 1. That is the equation number 7. Alternatively, flammability limits can also be computed using another equation. Alternatively, LFL can be given by minus 3.42 by delta Hc plus 0.59 or 569 delta Hc plus 0.0538 delta Hc square plus 1.8, and upper flammability limit can be estimated as 6.30 delta Hc plus 0.567 delta Hc square plus 23.5, equation number 8. One can also estimate the limiting oxygen concentration. LOC actually has units of percentage of moles of oxygen in the total moles. Actually, LOC is percentage of oxygen, or let us say percentage of moles of oxygen in the total moles. For hydrocarbons, LOC is actually estimated using stoichiometric relationship of the combustion reaction, which can be given by simply LOC is approximately equal to Z concentration of LFL. That is equation number 8. So, friends, in this lecture we discussed about the flammability characteristics of liquid, gas and vapor. We have understood what are the importance of lower flammability and upper flammability limits of a given mixture or a liquid. We have also seen how these characteristics vary with respect to increase in temperature and increase in pressure. We have understood what is the range of flammability which will actually be responsible for understanding or estimating the probability of fire in a given situation when all the 3 arms of a fire triangle are inherently present in a process system. We have also understood various methods and various empirical equations based on which the lower and upper flammability limits of liquid and vapor can be, or mixture can be computed with different empirical relationships, which we just now saw in the lecture. In the next lecture, we will discuss further more about the stoichiometric balance and how to estimate or how to actually draw a flammability diagram in detail if you know the properties of the flammability characteristics of a given liquid or a mixture or a hydrocarbon based upon the stoichiometric balanced equation. Thank you very much.